Hi, my name is Michael Ostroff, and I'm a PhD physics student from FAU. You probably know that, though, based on my previous appearances on this channel. So, in one of the said appearances, I was talking about something I thought I had discovered called metric ambiguity. The reason I originally came up with this was I was experimenting with different ways of defining the Levi-Civita connection in ways without using the metric tensor, and I was trying to see if that was compatible with GR. So I decided to do some experiments testing based on the equations and the Levi-Civita connection. And I thought that I had proved that you were able to use any Levi-Civita connection, and it would as long as it's symmetric, then you would be able to it would be equivalent to GR, and you could use that. But apparently that's not the case. So it turns out that there are Levi-Civita connection fields, by which I mean an affine connection you use for geodesics, which is symmetric and it's lower indices. It turns out that there exist Levi-Civita connection fields which are not metric compatible, i.e. there are no metric tensors fields in theory which can generate said fields. And correspondingly, there are Riemannian curvature tensors, mixed index form to be specific, which are also not metric compatible. The mistake in my proof for metric ambiguity, which was the idea that you could do gauge transformations or of sorts on a metric tensor field and basically change the local value of it, and that wouldn't affect the Levi-Civita connection field. So the idea, that idea was sort of rooted in equation 4 of my proof of metric ambiguity. The parallel transport of the metric tensor is inherently path independent, and what this means is that there's an equation for what you get when you parallel transport tensors around closed loops, and it involves the Ricci tensor. And for a metric tensor, which is a rank 2 tensor, you have to use two Ricci tensors with different indice permutations. And something that you do with this is this uses the Ricci tensor in its mixed index form. And when you're multiplying it by the metric tensor, this essentially lowers the contravariant index, and now you have two copies of the Ricci tensor with the first two indices permutated and they're added together. And because the first two indices of the Ricci tensor, or the Riemannian curvature tensor, I meant to say Riemannian curvature tensor, I'm sorry. Because the first two indices of that are anti-symmetric, this should inherently be it vanish. So, and that means that the parallel transport of the metric tensor is path independent. However, it turns out that if you have if you were to create some random metric tensor field and create the Riemannian curvature tensor at a given point, and you were to give that to somebody, it turns out there's generally only one choice of metric tensor at said point, which is able to lower the contravariant index such that the first two indices of the Riemannian curvature tensor are anti-symmetric. Well, there's also a scalar multiple as well. So essentially this means that if you give someone a Riemannian curvature tensor which was generated using a metric tensor, then they should be able to deduce what the metric tensor was at that exact point they should be able to determine what the metric tensor was there up to a scalar multiple. So basically, if you give someone a Levi-Civita connection field, which was generated using a metric tensor field, they can actually reconstruct the entire metric tensor field up to a scalar multiple. And so metric ambiguity is completely false, because the metric tensor is objectively not really all that ambiguous. This is the level of ambiguity that we had previously known about. We had already known about the scalar ambiguity of the metric tensor field, so this isn't exactly news. Apparently, if you were to take a random Levi-Civita connection field which wasn't generated by a metric tensor field. In general, the mixed index Riemannian curvature tensor field that it creates is not, like the first two indices are not going to be traceless. So if you were to like contract them in the mixed index form, it wouldn't necessarily go to zero, which is like that it's supposed to for the mixed index Riemannian curvature tensor. And even if you were to create your like random Levi-Civita connection field such that that was the case still, then that would still not be able, like necessarily mean that there exists a metric tensor field which can lower the contravariant index such that the first two indices are anti-symmetric. So this is a property of GR that are like the metric of our like universe or reality is metric compatible, which hasn't, I don't think it's actually been tested before. So that might be a potentially interesting test that you could do of like general relativity. And you could actually have a Levi-Civita connection field, which is Ricci flat, but not metric compatible. So this doesn't necessarily require extreme densities or anything. I'm not entirely sure if we like were to go out and like look for this, we would really find much like metric incompatibility. I mean, any measurements we do inherently have noise in them, and that noise will essentially mean that any Levi-Civita connection field we measure will not actually be metric compatible. But that metric incompatibility might be very small, though I'm not entirely sure how you would like calculate it. I don't have an equation for metric incompatibility. But regardless, this metric incompatibility, or this metric ambiguity that like I've come across, it actually caused me a lot of issues, to be completely honest, because I had been working on like my dimensional collapsar theory, which is essentially Kaluza-Klein theory, but like even like to like an extreme essentially. And I had a like model for like particles or particle sizes essentially, and those depended on the size of the compact space in Kaluza-Klein theory. And if like the compact space were to change size, then so would the particles, because like the dilaton like field like got larger, so it's like more space, and therefore like it's sort of rooted in like the fact that the metric tensor field or actually it's rooted in the fact that like vacuum spacetimes are like scale independent, so you can like scale them up or down, and there's like no effects really. So I was going to use this to okay, I should start over just like a little bit here. I essentially had this model for how dark matter worked using dimensional collapsar theory, where particles are Kaluza-Klein solitons, and they're essentially sucking in extended space-time and expelling it in the compact space, and this makes a dilaton field like elevated around particles, and get like low, like smaller and smaller with like greater and greater distance. And this dilaton halo I thought would be responsible for the effect of dark matter. And I was going to pursue research in this and like look into it more, and metric ambiguity kind of threw a wrench into that. But now that metric ambiguity is like dead. Oh, by the way, it was Dr. Beadle at FAU who pointed out like the error in my proof. So thank you, Dr. Beadle, for like helping me like figure this out. I'm eternally grateful to you. Anyways, I should have mentioned that earlier. Anyways, now that metric ambiguity is like gone, I decided to go back to this testing, and I decided to calculate what the stress energy tensor was, or the 4D stress energy tensor was for these dilaton halos. So what I did was I took the normal metric tensor for the Schwarzschild black hole. I did a Wick rotation on it such that instead of being like time like in the time dimension, it's actually space like. Then I added an extra time dimension, So, and I basically relabeled what was previously the time dimension as the dilaton field, so it's a compact space. And this is a type of Kaluza-Klein soliton, which has zero gravitational mass, which means that if you were to be traveling on a purely time-like trajectory as like a point particle in the 5D space, you wouldn't feel any attraction towards like black hole, or essentially, or the soliton. But it does have this like dilaton halo, and so I went and calculated the 4D Ricci tensor, and I used that to then calculate the Einstein tensor. And it turns out that this like metric that I was using for this like Kaluza-Klein Kaluza-Klein Schwarzschild black hole soliton thingy, I don't know the correct name for it. It turns out that it's a Ricci flat manifold. So this essentially means that the Ricci tensor and the Einstein tensor are exactly the same. And the stress energy tensor, I've only calculated in the fully covariant form currently. Haven't looked at it in the contravariant form yet, but it appears that there's this, it's like zero for the most part, so it's like diagonal. There's no time component to it at all. There's only like a radial theta and azimuthal components, and the radial component to the Einstein tensor, or I guess stress energy tensor as well, it's actually negative, and the azimuthal and theta components are actually positive. And it appears that the negative part grows weaker, faster than the azimuthal and theta components as distance increases. This is just for it in the fully covariant form. Not entirely I think this is probably still going to be the case in the contravariant, fully contravariant form, but I didn't get to that part of the calculation before this, so I'll have to make a Substack post on this as well. That and the metric ambiguity disproof. I think that this should generate a dark matter effect. It seems to line up, because as you get farther away, it's the metric, or the stress energy tensor, should be mostly positive. I'm not entirely sure. This is will generate a dark matter effect, but I'm mostly sure. I need to do a lot more testing on this. So I'm going to be doing more research on this Kaluza-Klein soliton and its Ricci tensor and stress energy tensor, and see if we were to observe something with the given stress energy tensor out in space, whether it would have this dark matter effect that we're looking for. And if it does, then that suggests that that's a testable prediction of dimensional collapse, our theory, and we should be able to find evidence of it in astronomical data. So first prediction of dimensional collapse, our theory, and hopefully there's evidence we can find of that. This reminds me of something that James Wells, when I posted my metric ambiguity disproof thing on the Wolfram Institute Discord, James said that he liked that about my approach, because I was willing to accept that I'm wrong on some things and move on. And that was essentially a core element of the scientific method, something along those lines. And the thing is, when Dr. Beadle disproved metric ambiguity, relatively quickly actually, and I was able to verify his disproof, I wasn't upset that I had been proved wrong. I was oh, thank goodness it's wrong. That was causing me a lot of issues. So normally when people make their own little pet theories, they like to go and defend them and stuff, and they want to keep them alive or whatever reason, for ego related reasons. But in this case, this was getting technically speaking, this was getting in the way of things that I cared more about, and it just going away just made me very, very happy. So I don't know if this is how applicable this is to other people's research. Thing is, I want to be right. I want to be correct. I don't want to feel right. So and not everyone's really like that, I suppose. So like, if I'm doing something and I find a disproof of what I'm doing, like, which tells me objectively that what I'm doing is incorrect and wrong, then I won't do it anymore. Like, or like if a theory gets disproven, I'll like just try to like either correct it or I'll just throw it out. But I'll try to be careful that I'm not like throwing the baby out with like the bathwater. Like I'm also afraid of doing that, because then I'd still be wrong and potentially even wronger than how I was before. So I just try to like modify what I'm doing to make myself as correct as possible. One thing I should probably do is model halo decay, because if you have these like dilaton halos which are generated by like mass distributions, if they undergo a like strong enough acceleration, then these dilaton halos should be capable of getting dislodged from their generating matter, and then they should like start decaying over time. And this is something you should be able to observe with things like the bullet cluster or similar like structures, because the matter distribution essentially collides with itself, and two dilaton halos then just go flying away without the matter that's generating them, and then they should be decaying. And we observe these we observe this like distribution of dark matter, and was like out any like matter around it to like, I guess like that's associated with it. And we could probably like figure out how fast these like halos are traveling and how much they should be like decaying over time, how big these halos were originally, and use like our like data from like the collisions of these like bullet like clusters to determine whether the like prediction of halo decay matches our observations. And yeah, so it's a calculation I still need to do, probably going to be very interesting, but I'd say it's looking promising. So math-wise, I had recently been reading a like fractal book in Dr. Han's office, and it had a section which was like fractals as solutions. And the idea was like, if you were to take something like the Koch curve, for instance, you can use it to make this like pretty little snowflake that's like a fractal. And essentially what it does is you take an image and you like perform these coordinate transformations on it, and you sum it together, and the result is like a new image. And like the Koch curve is essentially the solution to this, where basically the like start and like result are equal. And I realized you can do this with like mathematical functions in general. It doesn't have to be an image. So I could take a combination of poles and zeros in the complex plane, and I could just perform these like coordinate transformations on them, and I could like multiply and divide them together, and I could just keep doing that over and over in an iterative process. And eventually I should probably get something which looks like this like Koch curve, or Koch curve, whatever, I don't know how it's pronounced. And this should give a way to generate like fractal functions other than using fractal flow like I was before. And this can be generalized to L systems in general. And I'm really curious about how it's going to like turn out. I know an aspect of the fractal flow, which I think exists, but can't exactly prove at this point, is that you can sort of have it like flow into itself, where you can like have parts of the like fractal meromorphic function like flow around in a closed loop, and then the function can return to its initial state, but it looks like the individual components of it have flown like around. Like you could have like a point where the fractal is like spiraling out of, and another point where it's spiraling into, and you could probably make an animation of like that actually happening, where the fractal is emerging from one point and getting sucked into another point. I don't know if you can do that with L systems. I'll have to check it out. I know that L systems normally are a bunch of like, they're made out of a bunch of affine transformations, And I'm wondering if you were to add Mobius transformations into the mix, if that would change anything and you would be able to get like a similar kind of behavior with these like L system fractals as well. So something I should probably try doing is creating these like L system fractals in higher dimensions as well, or maybe just sticking or like doing some other stuff with like the one-dimensional like fractals still, so they can easily be visualized in the complex plane, and seeing like what behaviors and properties that they have, and how flexible the like generations of like fractals are with these approaches. I think this should actually be like very good for generating dendritic fractals, because I don't think that this approach should really generate fractals which are like fully connected, by which I mean you can have like the Julia set. If you choose like a value for the normal one, if you choose a value C which is on the edge of the Mandelbrot set, then, or actually it's on the Mandelbrot set exactly, then the Julia set should be like dendritic and like it should have an area of 0. But if you choose a point inside of the Mandelbrot set, like and like that blobby fractal thing, then the results will like the resulting Julia set will actually be connected. And if you were to look at the fractal flow of that, that would be a region where the fractal flow goes to complex infinity. I don't think you can get that with L systems. I'm not 100% sure though, but I think you might be able to get like dust, like Cantor dust, using an L system potentially, because I could imagine you have like a coordinate transformation which when applied iteratively just like takes the original function and just makes copies of it like spaced out like evenly, and that would technically like be a dust if the like original field, or if the original complex function were to be like a dust, I suppose. So yeah, I really want to like play around with that and toy around with the idea and see if like how well it works. I might hopefully I'll like sell some like art of this like fractal stuff soon, because I imagine it's gonna be like really pretty. So yeah. If you are good at like the theory of integrable systems, then I would probably like to talk with you, because I'm currently trying to learn about them, because I'm trying to see if I can reformulate general relativity as an integrable system. And I've been having like various setbacks, and I've like been learning like things about how it works. I'm trying to figure out like how many scattering parameters like a integrable system should have, if like you can have like multiple scattering parameters, and if like these scattering parameters can be like a tensor, like, because a scalar field, it's kind of like indistinguishable from a like a one-dimensional vector or covector essentially. And I'm not entirely sure what the generalization to like higher dimensional integrable systems is, if like there should be like several scattering or there should be several spectral parameters. What I meant to say spectral parameters before, by the way, I'm sorry. Like if there should be several spectral parameters, or if there should just be like only one spectral parameter, which is like a scalar. I'm trying to figure it out. I'm very confused in this regard. So if you're an expert, contact me, please. I don't know what the structure of the scattering data is, and I've heard that there is this like transmission and or like reflection components to it, and I've like kind of heard that those correspond to like regions in the like positive imaginary and negative imaginary part of like the scattering parameter. Like you can imagine the scattering parameter as like a coordinate system, and I feel that's like a weird dichotomy to have like it kind of like separated in these two parts. And I was talking with like like some AIs to try and like get a better grasp, like the AI's knowledge on this stuff is like questionable at the very least, so I'm not taking what they're saying like too seriously. But they mentioned there was a way to like combine this such that you have instead of being like wrapped, going from like negative infinity to a positive infinity on like the real axis, you kind of like correlate together such that the regions that you're like integrating over is like lies on like the unit circle, and the part which was previously the transmission or reflection stuff is either the region inside that unit circle or outside the unit circle. I forget which. And I'm wondering like how to solve the inverse scattering transform like in the general case, because I don't know how to do that. I don't even know how to do it for like simpler like integrable systems. Like there's a lot I need to learn in this regard. If the scattering parameter is a like corresponds to like a vector space, like a complex vector space, then I guess this higher dimensional like version of like the unit circle, I guess it'd like be some complex n torus. So like I guess it's some, I mean I'm familiar with like complex n tori based on my research on complex Riemannian manifolds, so like I guess I have some familiarity there. If you enjoyed this video, be sure to like it and be sure to share your thoughts about what my research in the comment section, and I'll try to respond. And if you want to learn more about what I'm doing, be sure to visit my active Substack and my YouTube channel of the names Perpetual Science.